All right, I'm here.
Nice.
I apologize for being tardy. Did you all see the news of the morning? The news du jour?
No. What's up?
No? Anybody?
The president of CI is moving to Northridge.
That's right. Give that guy a cigar. The President Beck, is leaving the university. That email went out this morning at 9:10, I believe, and it was news to absolutely everybody that I have talked to, all the faculty that I have talked to. I am the vice chair of our academic senate, and so we are trying to figure WTF to do. So anyway, it'll all be good. It's just a little bit of a surprise. So pardon me if I am slightly distracted today. Hey, but it's statistics. Let's talk about statistics. Statistics is so much better than politics and personnel. We have been talking about data. We've made that pivot to measuring data, sampling data. And we're talking about we're going to start talking about chapter 3 today. And as I organize my tablet here, does anybody have any questions they want to ask of me or of the class before we get going or while we get going? Any questions about stuff you read?
Oh, I have a question on one of the homework.
Yeah.
So one of the questions it asked for like the first and third quantile.
Yeah.
Or first and third quartile.
Yeah.
And you know how in R you do you just basically type in quantile?
Yep.
So when I did the quantile, it showed that the 25% quantile was like 21.5. But when I was like trying to do the first quartile by hand, I got like 21. Is there supposed to be like a difference with that?
Yeah, good question. Very good question. So describe how you did it by hand.
So there was like 16 data points. It was like the method A one. So for the quartile one, I chose I think it was the fourth and the fifth data point, which was, I don't have it right here, so
Yeah,
I don't really know what
cool.
the numbers
Yeah.
were. But I chose the fourth and fifth and I added them and then I divided by 2. And I think I got 21. But when I did it, the 25% quartile, I got a different number. So I was confused about that.
Yeah, so that's a great question. And as is the case in so many areas of statistics, there's lots of ways to calculate a percentile or a quartile or and so that small difference, right? The difference between 21 and 21.5, that's negligible, right? And 21.5, was that in your data set? It wasn't, because you calculated an average, right?
Yeah.
So the standard way, so I'm trying to think of how the book talks about it. A quantile is going to either be the element in your set below which you have that fixed percentile or fraction of your data, or it's going to be the average of the two. And so the book would say your answer should be 21, but R might implement it slightly differently. So R might say, well, this is where I'm going to take an average, because definitely I've got 25% of my data below 21.5. So don't sweat it when you get those tiny differences for quantiles. They're the same to most people.
Oh, okay. That's good.
Yeah.
Thank you.
You bet. Any other questions?
If you care deeply, I think R has a bunch of different algorithms where you can tell it to do it slightly differently.
Yeah, so if you type in in the console $quantile and hit return, a help page will pop up that shows you the required parameters that you have to give to quantile, which is basically just the x, right? The numbers you're computing quantiles for, and then all the options. And if you scroll down, it describes all the options, and I think that's what Patrick's talking about. There's tons of options for how to calculate a quantile that you can choose. So um, that's really beyond the scope of this course. It's good to know that they're there, that people can articulate precisely how to choose a quantile. So we remove that ambiguity. Is it 21 or 21.5? I'm not worried about those distinctions. It if you're a mathematician, you think, oh my God, I want to know what number it is. But just take a deep breath, step back and say, we're okay with a little bit of ambiguity there. All right. Any other questions? Not hearing anything. Let me share my tablet. And let me see, what was the last thing that we talked about? Anybody remember? What were we talking
Bivariate
about?
data.
Yeah. So the last thing we talked about was bivariate data. And we like looking at data. Data is a nice thing for us to see, being primates with these huge visual cortexes. And so I showed you how to do a scatter plot in R, okay, using the plot function. We will come back later to talk more about bivariate data. And we'll talk about what's called the correlation coefficient. And we'll talk about linear regression. And these are topics that relate to modeling data. And so I think our textbook has that in chapter 7. We're going to talk a little bit about inferential statistics first, and then we'll talk about regression. It's a very important topic in mathematics or in statistics. But today, I want to talk about error. Oh, I guess I should also say that last time we talked about, we had adjectives for describing data. Blake brought up the word quantile, which is a generalization of the idea of quartile or percentile, okay, median. And then we had the idea of the shape of a distribution or a shape of a set of data. So it could be skewed left or right, or it could be symmetric. These ideas of shape, skew, and symmetry, they're really qualitative. There's not a numerical measure that we'll talk about to quantify how skew something is or how symmetric something is. The closest we'll come to quantifying skew is comparing mean and median. If a distribution of data is symmetric, then the mean and the median are going to be about the same. But if this distribution is skew, then because the mean is susceptible to outliers or susceptible to large values, it gets pulled in the direction of the tail. So if we're skew right, then the mean is going to be to the right of the median. If we're skew left, the mean is going to be to the left of the median. All right. So let's talk about error. Okay, so let's do a 3, 2, 1, go exercise. All right. So I want you to think about what you've read about error so far, or what you know about error. And I want you to type into the chat. I need to find my chat window. Here it is. I want you to type into a chat a word that a textbook associates with the concept of error. What's an important word or important idea that's connected to the concept of error, according to the textbook author? So take a second, think about it. Type something into the chat. Only want one word. You might be able to think of 3, but just put 1. And then I'm going to do the 3, 2, 1, go, and we'll see what people say. All right. 3, 2, 1, go. Only 2 people are playing? Oh my goodness. So the 2 words that are thrown over there are propagation and approximation. So propagation of error. All right, that's something that's in, I think, section 3 or 4 of chapter 3. And we'll say something about it. There's a theorem about the propagation of error that we'll mention. So that comes up later. So Kevin mentioned the word approximation. Yeah, that's certainly a really important idea that we associate with the idea of error. In Calc 2, and maybe even in Calc 1, you learn that the definite integral of a function, it's approximated by a Riemann sum, right? And the error is the difference of those 2 numbers. So definitely error is associated to approximation. And in statistics, how is it that we're approximating things? Are we approximating things like this? We're coming up with formulas that approximate. Can somebody throw in the chat or vocalize how this idea of quote unquote approximation appears to us in statistics?
Well, we sometimes approximate like that, like with a binomial and Poisson, but we usually do it by taking a sample instead of a population.
Yeah, right. That's what I was looking for. A sample mean versus a population mean. So in statistics, we're always coming up with approximations. We're taking a sample and then computing something from that sample to try to estimate, some property of the population. So it's through this sampling. So Ashley just put into a chat another term, and that's bias. So is bias related to error? How is bias related to error? Anybody explain that?
Doesn't bias introduce error because when you introduce bias into sampling, you have an error when you look at your approximation. So it kind of is tied in with approximation, I think, because if you look at one specific part of the sample, or your sample is a very specific part of the population, there's error when you try to relate that sample mean or standard deviation to the population.
Yeah, right. So it's a limit. And this is the way I'm going to try to express what you said, Ashley. A limit introduced by the investigator. Either because she chose a poor sample or did something else that creates error in the data. Okay. Is that kind of what you're getting at, Ashley? Is that jibe with what you're saying?
Yes.
Yeah. All right. So I would say that as we head in today, this idea of bias and this idea of approximation are two key ideas to understanding error. Error is something that's always going to be with us when we do statistics. This is not a calculus course. In calculus, we'll eliminate error by taking limits. In stats, we can't eliminate it. So we need to understand it. So that's what I'm going to talk about today. So let's talk about sources of error, okay? And bias will be kind of in that picture too. So in statistics, basically what we're doing is that we're coming in and looking at data that was gotten through measurements, okay? And from this point forward, we're going to associate the idea of measurements with random variables. On the probability side, we associated them with this theoretical concept of experiments, like things that were happening. On the stats side, the experiments really are making these measurements from processes that are random. So the book makes this little equation that measurements are random variables. So I want you to take a second. We're going to play 3, 2, 1. 3, 2, 1, go again. I want you to take a second and think about what kind of measurements one could make that would lend themselves, to a statistical analysis. Now, let me make it easier. Let me broaden that up. I want you to think about and type into the chat one type of measurement a person could make, an investigator could make, or an investigator could be interested in. Okay? What's one type of measurement an investigator could make or be interested in? I'll give you 20 seconds to type something in, choose and type something in, and then I want people to hit enter. And I'm going to expect 12 responses in that chat because everybody can come up with something. You don't have to have read the text. You just have to be here. What's an example of a measurement an investigator could make or study? Okay, 3, 2, 1, go. We got 9. I will assume the other 3 people are not here. They're just logged in and they're off eating pizza. If you can't answer this question, there we go. Okay, that's fair. Brisa, that's fair. Okay, so I'm going to write down in my notes what I'm seeing here in the chat. So a quantitative survey question. So I'm going to say a survey question. And it doesn't even need to be quantitative. It could be qualitative, right? What color is your hair? That's a perfectly good survey question. Quantitative, like a height. So this is what I'm looking for, something specific like height. A standard deviation isn't a measurement of a phenomena. It's a description of data. So I'm going to skip over the standard deviation. A price, right? Exactly. You could absolutely look at prices. A length of time. Or a duration. Or maybe Alex meant an instant in time. So what time did something happen? That's good. So Glenn said sampling. So that's a sampling of something. I'm looking for the object of that preposition. A proportion. Okay. People's response to an ad online. So I'm going to say clicks. Times. Okay, good. So one of the things I'm going to add here is that if you're measuring proportion, then to measure a proportion, you have to count. And so a count is another type of measure. So can anybody else think of another thing that could be measured? Another type of measurement someone could take? Or Brisa, is this better? See what we're doing? Okay. So anybody else come up with another measure? Another thing that can be measured? Throw it in the chat. Orders. Okay. Like preferences, yeah, right. Distance or length. Our textbook is filled with examples of people measuring lengths of things or lengths of things, right? And think of like a science class that you've been in, right? Like in earth science, you might measure a density, or in physics, you might measure a density. Other things I came up with, a decibel. Anybody know what a decibel is? A measure of?
Isn't it sound?
Yeah, volume of sound. Yeah, so I'll combine your two. Yeah, like amplitude of sound. Amplitude of sound waves, right? I saw Kevin put in sound waves. And if we're talking about sound, what's something else that can be measured from sound? And Ashley, you know this, so let somebody else see if they can come up with it. Amplitude and
Frequency.
yeah, frequency. Measure the frequency of a sound. I'm teaching calculus, and I'm sorry, I'm getting close to the bottom. I'll just put it up here. Volumes and areas, you can measure those. Velocities, you can measure those. Speeds, velocities. There's all. So I'm just making this list here to show you there's all kinds of things we can measure. It's going to be easy for me to come up with examples where all I'm measuring are lengths and distances or something, and that'd be kind of lazy on my part, or lengths of time. But there's all kinds of things we can measure. And I will repeat, a lot of these things here are quantitative. They have a number associated with them. I guess orderings, I guess that's kind of quantitative. But we could also measure qualitative things. Eye color, hair color, primary ethnic background, categorical things. Those often might amount to counts. But there's some measurement that happens before we make a decision about a hair color or before we make a decision about an eye color, okay? So here's the idea, okay? So I'm gonna go from measurements to error. Whenever we make a measure, the measured value we get from our process of measurement, if we're lucky, it's equal to the true value, but it will never be equal to the true value unless we're lucky. And when we're lucky, we won't know it's the true value, because there's going to be bias introduced into our measurement, possibly. And there's going to be random error introduced into our measurement as well. So these things together are kind of the sources of error that I want you to think about. And it's not like we have to control them or eliminate them. We just need to understand them, right? So if we have an opportunity to, we can manage them. Okay. So let's talk about a couple of these things. We've talked a little bit about bias already, so I'm going to leave that for a second. Let's talk about random error. Where does this come from? So let's talk about sources of natural random error. Oh no, let's say just randomness. Because if I can identify sources of natural sources of randomness, maybe I can protect my measurement process from them. So does anybody know can anybody share one source of natural source of randomness? Anybody know of one?
Radioactive decay rates?
Sure. Atomic decay. And what's random about it is when it happens. When does a radioactive particle or a particle of radioactive element, when does it decay? When does it emit an alpha particle or a beta particle? So that's recognized as a genuine source of randomness. Okay? So if you're measuring something and that measurement is going to be interfered with by atomic decay or radioactivity, that might be something. If you can control radioactive decay around you or its effects, then that can help improve your measurements. What's another source of randomness?
Would gravity count?
How so?
If you were, something simple like throwing dice, couldn't gravity have an effect on that if the weight? I guess that's more of like the dice is weighted weird. I don't know.
So weighted dice would have more of an effect, but gravity is locally constant. So the effects of gravity here on me sitting at my desk is going to be the same as the effects of gravity on me if I walk out onto my porch, which is 5 feet away. So I think gravity is pretty constant. If you go to different places of the Earth, the force exerted by gravity is going to be slightly different. But I think when somebody at NASA uses gravity in their calculations or Earth's gravity in their calculations, they just assume it's constant. So the variation is very slight, and I wouldn't call that random. Somebody else? Digits of pi be random? The digits of pi are not random because the universe tells us what pi equals. However, if you put somebody somewhere and in the decimal expansion of pi and didn't tell them where, then the numbers would appear as if they're random. So I'll put digits of pi in there, but you got to choose where you start at random, and then the digits that follow from there would follow as if random. Anybody else have a natural source of randomness? And thank you, Kevin, for saying pi is natural. A mathematician is a Platonist. I appreciate that. How about this? Do you know what this is? Brownian motion. Anybody know what Brownian motion is?
It's the way dust particles move because they're struck by atoms.
That's right. It's the way dust particles move in space. If you look at a volume of air around you and zoomed in to look at how the dust particles are moving, they would appear to be moving at random because they're being struck by air molecules. And air molecules are moving around because of thermal energy, and that thermal energy imparts a randomness too. So I'll write that down, thermal energy. Okay, so Brownian motion, a classic source of randomness. Physics. What part of an atom is random? Anybody know what part of an atom is random?
The position of an electron.
Yeah. The position of an electron is described probabilistically. You can't find its location. We describe it probabilistically. It's random. In biology, something that's random. Any bio people out there? Ashley?
I'm thinking like dispersion through a natural environment. That's a little more random since you can't really predict or,
Sure, dispersion through space. People might say that a population of animals moves across a landscape and in a random walk. And so you could say dispersion would be kind of like Brownian motion in a way. I was thinking of genetic mutation. Genetic mutation is a source of randomness or is an expression of randomness. Some people connect that to atomic decay, right? Radioactivity, or that radioactive energy can harm genes and create mutations. I'll just write down some more. There's a phenomenon called electronic jitter in electronics. It just has to do with some variation in the electricity and charge in electronics that creates a random phenomena called jitter. Here's a good one. Survey respondent who does not answer faithfully. Right, a respondent who lies on a survey, that's kind of random, or it introduces randomness into your data. Or a survey respondent who doesn't understand the question. And so they answer it at random, right? If they don't understand it. So that's an example of a source of randomness, and it's a person, so it's natural. Yeah, so randomness can come from all kinds of places. A lot of time it's really small scale. A lot of these things we talked about are really small scale, but it can happen with human beings too. And when you're doing surveys, there can be a source of randomness there as well. All right, let's talk about bias for a second and what types of bias you can have. So bias is error that's the same for every measurement. Okay. So in the absence of a random error, your measurement minus the measurement value minus the true value equals your bias. So if you're always making the same error when you measure, you're never going to get the true value because there's always going to be this contribution that's in your bias. Your bias shifts your measurements away from the true value. So I like to think of bias as an imperfection in your system. And these imperfections are things that you can fix if you're aware of them. So the book, when it's talking about bias, the first example in chapter 3, it talks about is a person who measures the same rock 5 times and gets 5 different numbers. That's an example of a bias that's a measurement error. Something's wrong with the way they're measuring, or there's some flaw in the tool that they're using to measure.
If they're measuring it 5 times, they're getting different answers. I would have thought that would be random error, not bias. I'm confused.
I mean, part of it could be random error. That certainly could play into it. But there's this phenomenon that's called measurement error, and you can measure the same thing different ways and get slightly different measurements. I don't know if anybody, if Patrick, you've ever tried to measure the length of a piece of wood using a tape measure. And, there's this old adage that carpenters have: measure twice, cut once. And I can't tell you the number of times I've measured something twice and I've gotten two different numbers each time, maybe off by 1/8 of an inch or 1/16 of an inch. But it's a real thing, and that's not random error. That's something wrong with how I'm doing it, or the tool that I'm using to measure things. When I was in high school and I was take a science lab, the best scales that we had in our lab were these old-fashioned, like justice like scales, right? They had two pans and a bar that went between them, and you put the thing you were measuring on one pan, and then you had to put on little weights on the other pan to see what the thing weighed. And there's all kinds of ways to screw up measuring the weight of something or the mass of something that way. Today we've got digital scales, and the digital scales and being able to zero out the weight using a tare function that removes so many sources of errors when you're measuring something. It's great. I wish I had that when I was growing up. So those are examples of measurement errors. Another type of bias, another type of bias related error you can have are faulty assumptions. Okay, and these skew all the measurements consistently away from the true value. Measurement errors might be hit or miss. You don't know how much they're going to skew. You don't know how consistent they're going to be. But faulty assumptions are really pretty consistently skewing your measurements away from the true value. One example of a faulty assumption is if you were trying to measure the position of a star in the sky at night and trying to ascertain its, I don't know, I don't know enough about astronomy to talk about this example, but I do know about fishing, right? So if you're standing on the shore and you're looking into some water and you see a fish, you're not really seeing the fish, right? The fish isn't there because light bends, or water bends the light. And so the fish is actually somewhere else. And they call this, what do they call this phenomena? Refraction. And if you don't know about the refraction of life or of light, and you're measuring the position of a fish, your position will always be off because you don't adjust for the effects of refraction. Okay, so that's an example of a faulty assumption. So I talk about all these things because when you construct an experiment, when you design an experiment to gather data, you want to minimize this kind of bias. And the way you do that is through knowledge. Okay. You want to know what you're talking about. You want to know all the phenomena that could affect what you're trying to measure and factor that into your design. Okay. Got to understand the theory, the phenomena. Or you've got to choose the type of sampling that will reduce bias in your data. Either that's a simple random sample or a cluster sample or a stratified sample. And then you have to have procedures and techniques that reduce measurement error. Okay, you got to make sure you know how to use your tool. You can use it responsibly and consistently. Okay, so that's error. Bias, random error. Okay. You got to understand these things. So let's talk more about measurements. So there are two types of patterns in measurements that statisticians like to talk about. And one pattern is called precision, and another pattern is called accuracy. To a lot of people who haven't thought much about data, haven't thought about statistics, these two words are synonymous, precision and accuracy. But from this day forward, with you, these two words have a very different meaning. Okay? Precision means your techniques are good. Okay? And it also means, and because your techniques are good, your measurements agree with one another. They're consistent. Okay? That means your measurements of a single phenomena have a small standard deviation. Okay, all your measures are precise. They're going to be clustered together when you're measuring the same phenomenon. In contrast, accuracy means the measurements are unbiased. Okay, so that means that the average of your measurements will be close to the population average. The average of your measurements are going to be close to the real value. So you can be precise without being accurate. That's to say, you can be precise and biased, or you can be unbiased, that is accurate, but imprecise. Those are the four things that can happen. And I like to think of this with this little chart. So it's a chart that has 4 boxes. Either you're precise or not, or you're accurate or not. And I think of these in terms of bullseyes. So throwing darts at bullseyes. If you're accurate and precise, you're going to get your darts thrown right there in by the bullseye, clustered up together, a nice pattern right around the bullseye. But if you're accurate but not precise, it means that your shots, on average, they're at the bullseye, but they're spread out. Right? You're kind of getting in the neighborhood of the bullseye, but you don't have a good cluster. If, on the other hand, you're precise, but you're not accurate, it means that you've got a good pattern, everything's clustered together, but you're not hitting the bullseye. You're away from the bullseye. And then if you're both not accurate and not precise, that means your shots are all over the place. So that's accuracy and precision. Okay. Any questions about that? So one remark, I think, going forward with the textbook. The textbook has started to talk about measurements in the following way. So say what are we measuring? The length of a macaroni noodle. So the book might write the length of a macaroni noodle in this way. It might say it's 3.5. It's a little big. 2.5 centimeters plus or minus 0.25. So when the book writes something like this, I want to make sure that you understand that this number right here is meant to be the mean of the measurements of the lengths of the macaroni noodles. And this number right here is meant to be the standard deviation of the lengths of the macaroni noodles. And by writing it this way, we'll see this occurs multiple times. If you'll remember, we did an example where we looked at how much of a population was between or within 2 standard deviations of the mean. And that was about 68%. So for what it's worth, about 68% of the data will fall in that range of between 2.25 and 2.75. So this is a legit way to write it down. And if you go above the standard deviation or below the lower standard deviation, right, things are tailing off. There's fewer and fewer things in there. So this is a pretty good convention, and it's a convention that the book uses. Yeah, and I guess I also should have said this plus or minus 0.25 is a representation of the error, right? So standard deviation, which for us to this point, it represents spread of the data. We want to use this synonymously with the idea of error. So the greater the spread in a data set, the greater error we expect in our measurements. This shouldn't come as any surprise to you. It should make a whole lot of sense, but I want to make sure you explicitly make that connection in your mind between the idea of error and the measurement of standard deviation. And sometimes the book will use error when it means standard deviation. So just keep that in mind. I think it's very reasonable, but it might be unusual. So as we head, well, yeah, okay, I'll just leave that there. Which brings us to the topic of, back to the topic of random variables. We've talked about how if we've got a random variable X, that random variable is going to have a mean and a standard deviation that will denote this way, mu sub X and sigma sub X. What I want to talk about today, or talk about now, is how we combine these. What happens if we combine random variables, and how does that change their mean and their standard deviation? And there's sort of two types of combinations that I want to talk about. Well, there's actually one. There's two I want you to know about. There's one I want to talk about. Oops. Yeah. So if I take some constant, some real constant, I'll call them alpha I. And I have n random variables with the same, well, do they need to be the same mean? Well, no, they don't have to have the same mean and standard deviation. They could be different. Okay. I can ask, what is the mean and standard deviation of the combination of these random variables? That is, I make a new random variable by adding up constant multiples of these old random variables here. What can I say about the mean and standard deviation of this new random variable? I'll tell you what that is today. You'll see it and you'll say, well, yeah, of course, that's absolutely clear. The second thing that I want to mention to you, but we're not going to talk about it in detail, and it goes back to this idea of propagation of error that was mentioned in the chat early in the class today. So imagine capital U is a function of a random variable Okay, just a generic function, right? It could be squaring, it could be exponentiating, it could be doing, anything you can imagine a function from pre-calculus doing. U could be one of those or a combination of those. What is the mean and standard deviation of this new random variable? So there's a theorem called the propagation of error that will tell us what it is, but I'm going to just write down a little hint to help you make a connection. If and when you see that theorem, it relates to the change of variable theorem in Calc 3, where if you're doing a change of variable for an integral, you use the Jacobian to adjust the value of the integral. Well, this is what propagation of error is kind of like. I don't think we'll have to use that. I'm pretty sure we can limit ourselves to this special case for this class, but I wanted to let you know that you can really accelerate or pump up the analysis of means and standard deviations of more complex random variables. So let's look at this for now. Let's look at a simple case. So let A and B be real constants. And let's let X be a random variable. Okay, with mean mu and standard deviation sigma. Then suppose I create a new random variable by adding B to everything. So the question is, what's the new mean and standard deviation of this random variable? So think about it for a second. It's kind of an abstract thing to be thinking about. But if you're like me, when you think geometrically, I think of X in terms of a distribution. So on the left, if I have this distribution of my random variable, and I'm going to add B, what did that do? Well, that shifted my distribution up by B, if B is positive. So what does that do to my mean? Well, it just shifts it. So the mean of my new random variable, that is the mean of X plus B, is the original mean plus B. So this is something that I want you to recognize, that there's this linear relationship with means. If you shift your distribution up, you also shift the mean up. And said that way, it's kind of obvious. What about making a new distribution by multiplying everything in the random variable by a constant? Well, then what's happening? Well, this is what we call a scaling factor. If you've taken linear algebra, you've played with scaling factors a lot. We even talk about it some in Calc 1. So if I've got a distribution, I multiply the distribution by A, what's happening? Well, it kind of depends upon where 0 is. So let's put 0 there. And if I multiply everything by A, if A is bigger than 1, I'm stretching everything out upward. If A is less than 1, I'm flipping it around the origin. And if A is between 0 and 1, I'm compressing things. Right? So if A is between 0 and 1, I'm kind of compressing things down. And so that is going to move the mean. It is going to compress it in the same way. So it turns out that the mean of a compressed or stretched random variable is going to be that same scalar factor of the original mean. And this works even if A is negative. So geometrically, this shouldn't really come as any surprise. Now, what about the standard deviations of these? So go back to the first case. What's the standard deviation? Oh, that's a row. What's the standard deviation of y? Well, if I've just shifted my distribution up by b, I haven't changed the spread at all. So the standard deviation is going to be the same. Whereas down here in the scalar case, if I'm multiplying all my elements in my distribution by a scalar a, that's going to affect the spread. So for example, if my data was the set -1, 0 to 1, and if my a is 3, then multiplying my data by 3, I get this set, and you can see that data is more spread out. I would be increasing its standard deviation, and it turns out you just increase its standard deviation by the same factor. Oops. And generally say, actually, you say absolute value of A, because if you calculate the variance, the variance gets changed by A squared. And so if you take the square root, then you end up with the absolute value. So this is what happens when you take a random variable and you change it linearly. All right, so if you've got a linear function of a random variable, you're shifting up and transforming the mean, and the standard deviation, at worst, you're scaling it. Yeah. So an important example of this is the sample mean. Okay, so let's let x be a random variable. With mean mu and standard deviation sigma. So we want to estimate the mean of this random variable. And we're going to do that by taking n measurements from this random variable. So I'm going to say let xi be the ith measurement or sample from x. So just so we're clear, xi is really just a copy of x. So it has the same mean and the same standard deviation. So I'm going to take n samples. And I'm going to use the ideas that we just talked about scaling and adding. And I'm going to define a new random variable called x bar. And it's going to be 1/nth times x1 plus 1/nth times x2 plus 1/nth times x3, and so on up to 1/nth times xn. So you can recognize this as the mean of these n measurements. Everybody with me?
So that's big X bar, which is different from little X bar.
Yes, it is different from little x bar.
Okay.
because little x bar is something you calculate once you have made a measurement. What I'm now doing is I'm abstracting this back one step, and I'm treating each measurement as a random variable. I'm not taking a measurement. I'm treating it as a random variable. So this is going to be random. This is going to be random. This is going to be random, and so forth up to this. And you can't do this in R, right? In R, you have to give it a concrete number. You have to have taken the sample and then put it into R, and it'll calculate it. Here I'm abstracting it back one level. Does that answer your question, Patrick?
Yes, thank you.
You're welcome. So with this new random variable x bar, I can ask, what's the mean of x bar? And what's the standard deviation of x bar? Okay. And so we say these of the sample mean. What's the mean? What's the mean of the sample mean? What's the standard deviation of the sample mean? And heck, let's just put the variance in there because we can get the standard deviation from the variance by taking the square root. All right. Well, we know that, well, do we know this? I guess this doesn't quite follow from what we did before. But if I have two random variables with means mu x and mu y and standard deviations sigma x and sigma y, then it turns out if I add the two random variables together, the mean of that new random variable is going to be the sum of the means. And it turns out that the variance of the sum is going to be the sum of the variances. So the mean and variance work out very nicely. Turns out, if I look at the difference of the random variables, the variance of the difference of the random variables is still the sum of the variances of the two random variables. So using this idea and applying it to this, I can say mu of the sample mean is mu of 1 over n x1 plus mu 1 over n x2 all the way up to mu 1 over n xn. And now using the idea on the previous page about scalars or scaling random variables, mu of 1 over n times x1, that's my scalar 1 over n. So that's just 1 over n times mu of x1. Oops. And likewise for the rest. And I can factor out the 1 over n. Oops. And because all these samples come from x, they're all the same as x. So I've got n times mu of x. Those n's cancel. And the mu of x is just mu. So the mean of my sample statistic is just the mean of my original random variable. Is that what I expect? Well, yeah, I kind of want my samples, any sample mean that I calculate, I want that to be close to the mean of my population. So I hope the average of my sample mean ends up being my population mean. So yeah, this kind of makes sense to me. Let's look at the variance. What's the variance of the sample mean? Well, that's the variance. Oops, write down what the sample mean is. And I said that this is the variance of a sum is the sum of the variance. So we can rewrite this as a combination of variances. And then what? Oh, then that scalar comes out as a square. That looks very pretty. And then we remember that all of these random variables are actually the same. So those are all sigmas. So on the one hand, I can factor out a 1 over n squared because that's in every term. And on the other hand, I've got n of these sigmas. I guess I can just call it sigma. So this n cancels with one of the n's down there. So I end up with 1 over n sigma squared. So we conclude that the standard deviation of the sample mean is sigma over the square root of n. So this is interesting. This is interesting. So what this is telling us is that when I calculate the sample mean, right, the expected value of the sample mean is going to be the mean. We already talked about that. That seems reasonable. But what this other thing here says is that the error in the sample mean, the standard deviation in the sample mean, it relates to the standard deviation of the original population, but it also depends upon the size of the sample. And the bigger the sample you take, the smaller the error. That is, the bigger the sample you take, the closer your sample mean is going to be to your true mean. How close? Well, square root of n. That's the factor. So this is a important result for us. We'll return to this often. It's something I want you to keep in mind. And it follows from this algebra of mean and standard deviation, or mean and variance for random variables and the way they combine. So let's do a couple examples. The first, let's see, how much time do I have? Oh, I've only got a couple minutes. I'm going to do an example that uses the idea that the mean of the sum is the sum of the means, and the variance of the sum is the sum of the variances. And then next time I'll start out with an example that uses the sample mean. So for this example, there's an electronic component called a resistor. And suppose there's a resistor in a car alarm system. Whose working life has an average length of 900 hours and standard deviation of 30 hours. Let's find the expected life of 4 transistors or 4 resistors. Okay, that is, if we expect one resistor to last 900 hours, how long do we expect 4 resistors to last, right? If we have 4 resistors in our car and we replace them every time one goes bad, how long do we expect those 4 to last us? And then we'll also ask, what's the standard deviation of that estimate? So if X is the random variable representing the lifetime or the length of the life of a resistor, then the mean of X is 900 and the standard deviation of X is 30. We want to know what's the mean of 4 resistors. So if we add those up together, and what's the standard deviation of 4 resistors? So we know the mean is additive in this way. So that's 4 times mu x. Mu x is 9. So we got 4 times, or mu x is 900. So we've got 4 times 900, and that's 3,600 hours. So we expect 4 resistors to last 3,600 hours. How about the standard deviation? Well, let's look at the variance. The variance is also additive. So that's 4 times the variance of x. So the standard deviation is the square root of that. So we get 2 times the standard deviation of x. And the standard deviation of x is 30. So the standard deviation of the length of 4 resistors is 60 hours. So this is how we apply that simple theorem. All right, that's all we have time for today. I'm sorry I went over 2 minutes. Thanks for hanging with me. And next time I'll talk about the standard or the sample mean, and we will head into where is it? There's a section in chapter 4. Let me tell you what it is. .9. Okay. And I'll put an announcement on the Canvas site to make sure everybody knows that. Okay. We'll continue to talk about these sample statistics. Sample mean is 1. There's other samples. Okay, that's it. Thanks, everybody. Stay safe, stay healthy. Anybody doing anything fun for Halloween? I forgot to ask that question.
I'm going home to see my dad for his birthday.
Oh, hey, that's fun. Definitely not scary though. Yeah, I'm not doing anything fun or
No.
interesting for Halloween either. Trying to keep people away and trying to keep people safe. Okay.
Seeing people is pretty scary at this point.
That's true. That could be the scariest thing. All right. Thanks, everybody. And yeah, Haley, I saw your text. I'll hang around. We can talk for a second. I'll stop recording.
Thanks, Dr. Miller.
You bet. See you, Ashley.